Hello everyone, today we will continue the last video and continue to explain what network equipment is.
There are many different technologies involved when using an EDU 2.11 wireless network. We start learning from the frequencies that are being used. You'll typically see Protocol 11 networks operating at 2.4 GHz or 5 GHz. Sometimes, in certain situations, both methods can be used on the same access point. Some of these standards even support communication over additional frequencies, although this may not be your common scenario. We tend to refer to these portions of frequencies used by wireless networks as channels, rather than using specific frequencies in the 2.4 or 5 GHz range. These frequency groups are numbered and assigned by the IEEE. If you're on a 2.4 GHz network and it's channel 6, it's always the same channel 6 on all IEEE 802.11. 2.4 GHz devices. Channels can overlap, which is why it's best to use frequencies on multiple access points that don't overlap or conflict with each other. The frequency range we can use depends on the channel width. Sometimes called the amount of bandwidth or frequency used on an 802.11 network. You often see 20 MHz, 40 MHz, 80 MHz, and 160 MHz bandwidths. This is what we mean. We discuss the bandwidth and number of frequencies available in the 2.4 GHz range and the 5 GHz range. Let's discuss specifically the 2.4 GHz spectrum that our ATO 2.11 network is using. There are 3 non-overlapping channels in North America: Channel 1, Channel 6, and Channel 11. They are grouped into 20 MHz blocks. If non-overlapping channels are used, there are 3 separate 20 MHz blocks located in the 2.4 GHz range between 2412 MHz and 2482 MHz. When we introduced the 5 GHz range, we also introduced a large number of available frequencies. Everything that's not read here can be used in 802.11, and you can see that there are more frequencies available in the 5 GHz range, certainly more than the 320 MHz non-overlapping groups we might have at 4 GHz. Not only do we use these 20 MHz channels, but some of these wireless standards allow us to use larger bandwidths, such as 40 MHz bandwidth, and while increasing the total amount of bandwidth, we use more of the available frequencies. We also have some standards that support 80 MHz bandwidth. This will allow you to see the different channels and frequencies available. Finally, a very large 160 MHz bandwidth. When you get this big, you can see that on the 5 GHz spectrum, there are only 2 contiguous 160 MHz channels available, 2.11, B, and G. The channel bandwidth used is about 20 MHz for A, 22 MHz for B, 20 MHz is 2.11 G. When we bring a 2 to 11N, we increase the options for the bandwidth we can use. For example, we can use 20 MHz, 40 MHz, or 80 MHz channel width. Some of these channel widths are apparently only available when using the 5 GHz frequency. For example, we do not have 80 MHz available in the 2.4 GHz range. We have to use 5 GHz to support larger bandwidths. 802.11 AC also uses 20, 40, and 80 MHz channel bandwidths, but also allows us to bond discrete independent 80 MHz bandwidths together. Of course, if you use the backward compatibility of 802.11 AC to connect 8 to 11 options, then of course we can use a contiguous 160 MHz bandwidth in the 5 GHz range, then you only need 40 MHz of channel bandwidth. But natively, 802.11 AC devices require at least 80 MHz of bandwidth, with the option to increase the channel bandwidth to 160 MHz as part of the standard. Whether you're connecting to a separate 80 MHz channel or using a continuous 160 MHz channel and an 802.11 behavior. This standard uses the exact same channel bandwidth as 802.11 AC at 20 MHz, 40 MHz, 80 MHz, 2 bonded 80 MHz channels, or a single 160 MHz channel. In a lot of conversations about 802.11, you often talk about an access point or a wireless router or some other infrastructure device that sits in the middle of the communication. But 11 also supports the ability for 2 sites to communicate directly with each other without using an access point of any kind. This is an independent basic service set, or IBC, that uses ad hoc or direct communication between two devices. Ad hoc means we create this connection for a specific purpose, and we don't have to plan or implement some type of access point to communicate. This ad hoc communication can also be permanent if only these two devices are on a specific network and no access point is needed. But we can also use ad hoc communication temporarily to configure separate devices and allow them to connect to devices that have access point wireless network. We will connect the device via a temporary connection. We will assign it the correct configuration of the access point in our area and then restart the device, and it will connect to the wireless network through the access point. When you connect to a wireless network, you'll notice that there's usually a name listed in the operating system. This can be a network such as SGC1 or a guest. This wireless name is called the SID or Service Set Identifier. We usually call it the wireless network name. However, if we are in a larger organization, the name of the wireless network is the same no matter where we go or what building we are visiting. Obviously, no one access point supports all these different buildings. Yes, there are multiple access points. They all have the same side name but different BSIDs or basic service set identifiers. Think of it as the physical address or media access control address of that wireless access point. So when connecting to this wireless network, you're typically just using the side, which is actually the MAC address or BSID that's connected to the access point, and most organizations don't just have a single access point. In many cases, they may have dozens or even hundreds of access points spread across many different parts of the organization. This is why we usually use the wireless name to connect to a wireless network instead of using the MAC address of that access point. By using wireless names, we can move more easily from one access point to another as we move through the building. When we share a network name between multiple access points, we call it an SID or Extended Service Set Identifier. If you connect to the east end at one end of the building and start walking through the building, you may find yourself roaming or automatically switching from one access point to another. It all happens behind the scenes. You don't know the switch is happening. All you know is that you are always connected to an access point that provides you with connectivity. We have a network switch on top that connects to two different access points. You can see that these access points have very different BSIDs and very different MAC addresses associated with them. The two access points are two separate physical devices. They share the same SID. Both of these are on SGC, a wireless network. There are devices in both areas of the building communicating with any access points local to them. In a building, a mobile device connects to one access point, then walks to the other end of the building, and you find that you are no longer able to connect to the original access point. If there is an access point closer to you with the same SID, behind the scenes, your device will automatically connect to this access point because it is configured with the exact same SID that you originally connected to. We can configure the SID and security information to be the same, and the devices will automatically and correctly roam to the access point closest to them wherever we go. We support very simple MIMO or multiple input, multiple output, and a 2 to 11 AC. Support for downstream versions of multi-user MIMO. To enable .11x, both downstream and upstream multi-user MIMO are supported to be able to send and receive information simultaneously. We need to have the right number of antennas and support. If you're looking at a wireless device, you'll probably see that it supports 2x2:2 2x4:, where the first number refers to the number of antennas on the access point that we put in the X, and then we refer to the customer the number of antennas on the terminal. Following the colon is the total number of streams supported by the device. You can have 2 antennas in the access point, 2 antennas on the client, and have overall support for 2 streams for that particular access point. There may be 3 antennas in the access point and 3 antennas on the client, but the device may only support 2 separate multi-user data streams. Or you might have a larger device with 4 antennas. For an access point, you might have a client that has 4 antennas on it, and you're able to support for separate streams on that access point. This multi-user MIMO is a great addition to the 802.11 standard, and before 11n is adopted, we will finally have one access point and one device, and we will be able to send information from one device to another without any operation. The working principle of MIMO is completely different from that of multi-user functions. We can use multiple antennas to send information between devices. The data bounces off other nearby devices but eventually reaches an antenna in the receiving device, and advanced digital signal processing is used to reconstruct the data. When we introduced MIMO, we were able to send more traffic between two devices. Multiple flows use multiple inputs and multiple outputs. We may have an access point that sends a lot of information to the laptop. Large amounts of information can then be sent to mobile phones, and large amounts of information can be sent to streaming devices. When the device needs more data, it can send it all using multiple inputs and multiple outputs. When we introduced multi-user MIMO, we were able to separate these streams so that we could send information at the appropriate rate based on the type of data needed. An access point that supports multi-user MIMO might have two streams that are constantly communicating with the laptop. A single stream that communicates with a mobile phone, and another stream that communicates with a streaming device such as a TV. These can all run simultaneously with multi-user functionality, and it takes advantage of multi-input, multi-output multi-user MIMO, i.e. 802.11 AC can also send different traffic in each of them. Mobile phones don't require as much data as laptops, but with 902.11 AC and multi-user MIMO, the entire traffic flow is required to send data to the mobile phone. Mobile phones may not need all the bandwidth to send data more intelligently through these multi-user MIMO networks. We can use 802.11ax, which introduces OFTMR, orthogonal frequency division multiple access. Here we can send multiple data streams, but we can split these data streams into smaller parts and send only the data required by the individual devices that require more bandwidth on the laptop. We can send these portions of data in a stream, feeding that information to a laptop, and simultaneously feeding the mobile phone and TV, meaning the site can receive exactly the right amount of data and use radio frequencies efficiently to support this. It also means we can have more users communicating simultaneously on the same 802.11 wireless network, supporting greater user density from a single access point. The antennas included on traditional access points are omnidirectional. This is common, and you will see them when you buy an off-the-shelf access point, and the signal is evenly distributed on all sides of the antenna. This is where we get omnidirectional from omnidirectional. This is a good option when you place the access point in the middle of a building and want it to have the same coverage evenly around the access point, but this doesn't give you a lot of options for focusing the signal. To get a very directional L1 signal, you need to use a different type of antenna. Directional antennas allow you to focus this signal and are often used when you need to extend your 0 to 11 wireless network over longer distances. Data can be sent and received over this single connection, and it's common to use these directional antennas between buildings. The performance of this antenna is usually rated in decibels. If you double the performance, you increase the decibels of the signal being sent or received. And using these measurements, if you increase the signal strength by 3 decibels, you effectively double the signal's power. Antennas like Yergi are very common. They don't take up much space. They are able to send messages in a very targeted manner, often resulting in very high returns for you. If you want to send information over longer distances, you may want to use a parabolic antenna, which has a higher gain and focuses the signal to a point. The signal will bounce off the parabola and into the front feed horn, allowing you to focus on that signal and...
Okay, that's it for today. See you next time.